So here's what we asymmetric carbon is this one. Okay? Not that that's that difficult yet, I don't think, but you got to get that down. Make sure you understand how P or L is determined. This little math exercise, I guess, but you just count the number of asymmetric. Of course, you didn't have the right answer for asymmetric carbons. You won't get the right answer here, but you just put in that number of asymmetric carbons as exponent, and your answer. Okay? And then the Fisher projection. For ketosis, you can do one of two things. I didn't put any of those on here for some reason. Say we have a sugar that looks more like this. For these, you guys can do one or two things. You can just do your Fisher. It gets a little weird up here if you have an O. Well, that OH doesn't really matter, but you would say that's a circle. Right? Our CH2OHs are circles. This you can either just show that way. That's kind of what's usually done. Or I'm saying you can use a triangle as well. So let's do the alternate. Right? You do a triangle there for your double bonded O. Okay, and then you do everything else the same, right, left, and this one is another circle, right, that's another circle. So these symbols have some meaning, right, the circles and the triangles, not just that you put a triangle on top always and a circle on the bottom, right, they mean something. So the circle tells us is a CH2OH, the triangle tells us is a C double bond O. Okay. But you can write it that way as well. Hey, just come up here. I didn't give you any of this. You okay with this? That's mostly how we're going to be dealing with these things. Well, you see today it gets a little more complicated than that, I suppose, but because we're going to use different kinds of Hayward projection. I asked you these kinds of questions when we have a test. I'll be asking you this. Some of you get a little bit confused. I heard some people talking here. In fact, I didn't really need you to name it. In fact, some of these you probably wouldn't know how to name, or just made them up. Maybe they don't even have a real name that you can find. But you're looking to see if an aldehyde or ketone. You're looking at the 7 categories they gave you in your notes. A couple of those we really haven't talked about enough. You wouldn't know what they are yet. But out of the ones we did talk about, I felt like these are ones. Everything we've studied so far are monosaccharides. Maybe you wouldn't know that, then you wouldn't put that in there. But you should be able to tell us D or L, count the carbons, tell us now those are ketose. Okay? We'll add into this. I do this like on a test situation. I'll put 7 lines. That doesn't mean there's 7 things. There are 7 choices, right? There's 7 things that it could be, but many of these categories don't apply all the time. Or for now, we don't even know what they all are yet. Like alpha and beta wouldn't apply to these, for instance. All right, so then this is just really comes mostly either from the notes or that big table really is where I think you can find all of these. I was using a little bit of vocabulary. Okay. And pectins, if you look that up, I don't know if anybody does any home canning, but pectins are what make jelly. And certain fruits like apples have a lot of pectins. Quince have a lot of pectins. They're often added in with other things, or you just buy pectin by itself and add it in. Because a lot of things you just want to really gel up and then you have more of a syrup than you want to jelly. All right? The models are pretty important that we did last time. Remember, you guys are gone. We had the bands, the trip. you have time, you might work on that and give you one, maybe work together even on it today if you have some time in class. Or I'll just give you a blank one, you guys can draw them, or you come in and do it some other time. Seeing the models is the best thing, and doing them, building them is the best, because you're going to have to do that when we have a test. Again, partly because some of you weren't here last time. Before spring break, we're actually going to have a test, so that's not very far from now. It's only a few classes, really. We're going to have class twice next week, and class 2 times a week after that. So there's only like 3 more classes in between, so it's kind of quick. But we'll have all the information that we're getting by then. And then I'm going to start calling this like a little lab test afterwards. After the break, we'll just do a 2-day lab, and it goes where you guys identify unknowns. You're going to how to identify them in 1 day, kind of work on groups, and then the second day you're going to work alone and get your own unknown and tell me which one it was. We'll see if it does pretty well on that. And then we'll be done with this unit. But we're going to split it up between the spring break. And we do have this day, Monday, April 2nd, which we thought would be a day off. And I haven't had this confirmed that it's actually a white day, but it wouldn't make sense that it's not, because that's the snow day we miss from a white day. I don't know if some people think we should make it a red day. I don't know if we want to do that. But if they do, then we wouldn't have school that day, right? We'd have to change things. But for now, at least, that's our makeup day. Shortens our break a little bit, I'm afraid. I don't like it. I'm kind of planning on that day myself. All right. Well, so you guys picked up some notes today, and we're going to run through those. Things get a little bit trickier, as you can guess, and get more and more difficult as we go on here. Starts out a little bit easy. So it turns out that a lot of our sugars will form rings under the right circumstances. Not in a solution, really. Yeah. Stop. Yeah, I'm making this up.
Oh, okay. Mr. Lingo has been creating chemistry all of these fictitiously.
Yeah, fake chemistry.
Fake chemistry. Stop.
All right. These names are super important. Well, they are kind of important. You're going to see them and use them a lot. But a pyranose is a ring that basically is a 6-member ring with an oxygen in it. Heterocyclic, it has more than one element in it, or 2 different elements. A pyranose is a 5-member ring. 4 of them are carbons, 1's an oxygen. 5 of them up here are carbons, 1's an oxygen. The double bonds don't really matter. In fact, you don't see those in our sugars. But when we say the word glucopyranose, that means we're going to be referring to the ring form of the sugar rather than the straight chain. Okay? Now, sometimes I make mistakes, you guys are pretty good at picking them up on for me, but generally, if I say glucose, I want you to draw the straight chain. If I say glucopyranose, I want you to draw the ring. Okay? I sometimes forget, and then you say, which one do you want? So here's what happens. This is kind of complicated. It's important you guys see how we number our carbons. 1, 2, 3, 4, 5, 6, right? We start up here. That's our number 1 carbon, our carbonyl or aldehyde carbon, and work our way down. So this carbon, what's unique about this carbon? What's it determine? D or L, yeah. So the D or L determining carbon, the OH on that carbon, we end up forming a new bond. What happens is this double bond of this O actually opens up. So here's just a straight chain. This is one I showed you guys last time, and we're going to change it. And here's something kind of interesting about this opening up, because it could open up with that O just the way it happened to go that way, or it's possible for it to open that way. Both of these happen, and we get different results. You wouldn't think that would make a difference, but we get a different result depending on which one. I'll leave it that way. And then here's the part you have trouble remembering. When that opens up, the H from the 5th carbon, the D or L determining carbon, the H joins that O that we just opened up to make an OH out of it. And the other 2 bonds that are still open join together. And now we have our ring. And you'll notice that in this particular case, that 6th carbon is the one that's not part of the ring. There's 1 carbon that's just not part of the ring, this one. here's our numbering, right? You can tell this by the bonds I use, that's our number one carbon. That was the one that had the double bonded O on it. 2, 3, 4, 5, 6 jutting out. So our actual pyranose ring, well, it doesn't really include that one carbon. Doesn't really matter, but you need to see what happens with that. Now, when you look at these, you have to look at them a certain way. You know how I told you guys you have to look at the straight chain ones the right way, right? The OHs and H's have to be pointing out at you when you determine if it's left or right. If the OH is on the right or the left. Well, you want to look at these a certain way too. And the way to do it is like this, where the sixth carbon is up and out to the right. And your number one, I'm sorry, that's not the way to look at it. That was backwards. Your sixth carbon is out to your left. One is sticking out. And your number one carbon is starting over here on your right and away from you. And this O is out, okay? You wouldn't really have to look at it that way, it's just that we always draw it a certain way, and that's the way we draw it. There's nothing really wrong with looking at it that way. Look, it's the same molecule, right, it doesn't change. But it's much easier to tell what you're doing when you're looking at this one, when you're naming them or determining some other aspects of it. So I want you to take a look at what happened to this OH that we formed, this new OH. Well, even before we do that, is this a chiral carbon? No, because it doesn't have 4 different things attached, right? It doesn't even have 4 things attached at all. But look at what happens to that carbon. This carbon now is a chiral carbon. Because we have an H, an OH, we have an O going that way, an ether group going that way. We have this carbon group. Those are different groups. I mean, they end up being the same, they're attached together, but when we go one way, it's different than going the other way. We've added another chiral carbon now. So now we have 2 more possible isomers. Yeah.
How would you determine if one of the rings is D or L? Or what
Is that the D or L?
Right.
The D or L comes from the way it started. Okay. And the one I chose must have been L. Because what happens with the sixth carbon is, when you're holding it the way I'm telling you, here's the plane of my ring, right? I'm holding this oxygen out away from me. You see how when you compare the H that's attached to the 5th carbon and the whole carbon group itself, this carbon's down. Okay, I'm not going to finish that idea, but I'm going to come back to it. I also want you to see that this OH, I'll just say together here, will it? This OH that we formed in the same way is also pointing down. Now, it's easy to say, oh, it looks like it's pointing up, right? Because H is pointing up. You have to compare this H joined to that hydrogen, or carbon rather, compared to this OH. That's the down position compared to this position, that's the up position. And we want to look at all those aspects of these. Look at this H versus that OH. In a way, it just sticks straight out. But comparatively speaking, the OH is down compared to the H, right? These can be manipulators. We're easy to see if you change it a little bit, but it doesn't always look like that. Same with this one. This OH is down, as it turns out. This OH is up in the up position compared to that H. And our 6th carbon is down compared to where it could be up in this position. All right, I want to go back to where we were with this. And I'm going to break this bond again. Okay, I'm going backwards now. I'm taking that H off. And I'm going to put that back here. And I'm going to make my straight chain from that. So, if you remember that new OH was pointing down. So here's a 1, 2, 3, 4, 5, 6 carbon. We're still going to form our ring, but I'm going to change it so now the O is on this side. It was over here last time I opened it. It was stuck here. Now it's over here. And when I do the exact same thing I did before, I take this H off and add it to that, put my bonds together that are open. We form a ring, just like we did before. When I look at it a certain way, with the, I did something wrong there. I used the wrong carbon. Sorry, I'm going to go back a step.
First.
I went to the 6th carbon, not the 5th. So I need to go to the 5th carbon. Oops, where'd that come from? All right, now maybe something change. I hope this didn't change what I was trying to show you, but, all right, yeah, that's all right. I'm gonna go to the fifth carbon down here. The H comes off, makes our OH. We join, we make the ring. We have the sixth carbon out of the ring. Right, we have this new ether group that wasn't there. So we've got this sixth carbon now. And notice it's still sticking down. That's because it was an L straight carbon chain to begin with. This one's also pointing down, which means I didn't do it right. So I'm going to redo this again. So we're going to open this back up. We're going to take that hydrogen off. And what I'm trying to make this do is, instead of opening so where the oxygen is on this side, it's going to be on this one. So I'm just going to change that. That's all I'm changing. Now I'm going to put my H back on. Put this together. Okay, now that new OH that I just formed is sticking up. So depending on how that double bonded O opens up,